Good morning, everyone. I think we can now start. There are more or less 15 people here in Parma, and some more are expected to arrive later. I see that more or less the same number of people are connected remotely. So it is my pleasure to introduce you to this second day of conference. Today we start with a keynote speech. The keynote speech is delivered by Marco Lippi. Marco Lippi is an associate professor at the University of Modena and Reggio Emilia. His research interests span from the machine learning to artificial intelligence and natural language processing. And today he will talk about neuro-symbolic learning and reasoning for natural language processing tasks. So Marco, please, you can share your screen.
Thank you, Stefania, for the nice introduction. Can you hear me?
Yes, we can hear you.
Okay, so I will share the presentation. And thank you to all the organizers for inviting me.
Thank you for accepting. Okay, we can see your screen now.
Yeah, I need the full screen. Okay. So what I will talk about today is quite a hot topic in artificial intelligence in recent years, and it's a topic that is an intersection of many research areas, and it has to do with a combination, basically, of knowledge with deep learning, or in general with neural architectures. So I hope it will be interesting, especially for the CILC community. Let's first review a few concepts that will help us through the talk. So clearly, it's a very well-known dilemma in artificial intelligence, long-standing dichotomies between connectionists and symbolic approaches. So how is knowledge represented in human mind? And we know that there are these two families of approaches. Clearly, this is a question that not only a computational question, but it goes into neuroscience, into biology, cognitive psychology, and still there are these two families of works. One is based on symbolic approaches, where reasoning basically is obtained as the result of the manipulation of symbols. So clearly, this is based on logic. On the other hand, we have connectionists, or sometimes also called sub-symbolic approaches, which are inspired by the human brain. And in that case, reasoning is the result of computation of some simple units that are interconnected between them, or even networks of some of these units. Clearly, I already said that symbolic approaches are founded on the principles of logic. They can exploit easily background knowledge. If a user has a knowledge of a domain, can easily express this knowledge in the form of predicates, in the form of rules, and can use all the instruments and tools of logic to deduce or induce new knowledge. And of course, a clear advantage of symbolic approaches in general is interpretability, because logic is highly interpretable, it has been studied for thousands of years by humans. Here is an example where, for example, we have a molecule that is described by predicates. Bonds and atoms are described by predicates, and we can write down a rule, for example, that says that this molecule is toxic because it contains several components, several parts. On the other hand, we have connectionist approaches. Connectionist approaches can more easily than logic deal with uncertainty, so with probability, with statistics, which of course is not so easily usable in pure logic. Connectionist approaches can be easily distributed as for computation here. And this is not a trivial point, because we know that recent progress in the area of deep learning has been fueled, in a sense, by the use of large data collections. Clearly, on the other hand, these methods based on neural networks, deep neural networks, but not only deep neural networks, are seen very often as black box models, because they are not explainable. And so to train them and to obtain performant models is a task that requires some skills that you can acquire with experience, that sometimes are not so easily transferable between tasks, not so easy to interpret, for sure. We all know that deep learning in this context has brought a revolution to AI. We cannot deny that. Here I wrote that has brought back a revolution into AI, because actually some of the novel approaches that are being used nowadays, and that have become the state of the art in so many application domains, are in fact old models that have been reproposed, and that have been maybe adjusted with the new techniques. Maybe optimization methods have been refined. There have been, on the theoretical side, something more has been learned, clearly, but a lot of the past has been reused. I'm thinking of convolutional neural networks, for example, which were known in the 90s, or even recurrent neural networks that can process language or sequences in general. There is a lot of applications that have been built on top of deep learning models. They have been able partially to use unsupervised data also, although this is still something that has to be explored more and more extensively. Which field have been so much revolutionized by deep learning? The list is very large. Here I mentioned speech recognition, computer vision, natural language processing, but nowadays we have in our smartphone a lot of applications that work on neural networks. We don't know that, but you know, when our camera captures, recognizes, detects a face, or when we ask Google Translate to translate something from one language to another, we are using deep learning without knowing it. So one question could be, and has been recently, is deep learning the solution to everything in AI? I am not the only one to believe that this is not the case, clearly. We know for sure that for many tasks, it's very difficult to compete with such approaches. And here I'm thinking of basically pattern recognition tasks, where you have to, you know, recognize shapes in shapes, and I'm not only thinking of images, but shapes in a signal, or in a text, or in an image, or in a video. And in many cases, research in this area is driven by big companies. They are playing a major role. They have resources that research institutions can only imagine, can only dream about. And so in this case, it's very difficult to compete, to beat the state of the art, in a sense. And the good thing is that clearly there is a huge space for application upon deep learning systems. So many domains have been influenced. But there is something that appears to be missing. What is missing in this picture? What is missing is basically what we often associate to the word reasoning. Okay, so being able to reason, to construct, infer new knowledge from a set of given knowledge, and to continuously learn new concepts, new ideas, and to reason about this knowledge is a task that humans are able to do easily. Even kids are able to do. These kind of networks are so good at recognizing patterns, but there is still a lot to be done to make such approaches perform also these reasoning tasks. There are many reasons for this. Clearly, I already said that these models, these deep networks, are very often black box models, so they're hard to interpret. And there has been some effort actually to try to investigate the inner structure of the networks, so the behavior of the network throughout learning and also at inference time, to see whether these neurons that are being activated can be associated to patterns, to symbols. This is called representation learning, for example. But clearly, one of the goals is to make these models interpretable. So this is very, as I'm sure most of you know, if all of you know, it's called explainable AI. So to make artificial intelligence models in general, and especially deep networks, interpretable by humans, so trustable. This opens a large research area that will be, I'm sure, investigated a lot in the future. But so how can we connect? How can we combine neural approaches with symbolic approaches? This is the focus of my presentation. This is not a new question, actually. Even since the 90s, there have been some pioneering approaches. One of the most known ones is called knowledge-based artificial neural networks, proposed by Towell and Sharlick in 1994. And it's actually one of the first attempts to inject knowledge into neural networks. What is the main idea? The main idea is that we have both a bunch of training examples, but we also have some symbolic knowledge, given, for example, in the form of rules, of logic rules. Now, the idea of knowledge-based artificial neural networks is to basically use the rules to build an appropriate network. So to have the network have a specific structure. Okay, and this is done by associating parts of the knowledge base to the architecture of the neural network. So, for example, final conclusion of the reasoning process will be associated to output units. Supporting facts will be input units, because it's what we observe. And we will have hidden units as intermediate conclusion of the reasoning process. And the weights of the network will model the dependencies between all these variables. Here is an example that I think maybe will clarify how the process works. So, for example, we have a conclusion named A that we want to infer, okay, from given knowledge, and we know that A is true if B and Z are true. So you can see immediately in the box below that this can be transformed into this junction where B and Z are two connections towards. Sorry, not a conjunction. So if B and Z are both true, then A holds. Okay. In turn, we know that B holds if, for example, C and D hold, or, and here is a disjunction, if E, F, and G hold, and so on and so forth. And from this initial collection of rules, we can, need to perform some transformation, but we can build a network, okay, sort of a tree structure where the bottom, the leaves, if you want, of this tree will be the input of the neural network, and which are the variables that are always on the right-hand side of the roots, okay, because they only used as input. You can also exploit the negation by using a weight with a negative value, for example. And once you have built this network, this can be trained with the standard algorithms, with backpropagation, for example. Now, this model was proposed, as I said, now over 30 years ago, close to 40 now, and it was, applied to a few toy problems and a few simple closed and small size domains, but it was the inspiration for many other research to come in the coming years. From these pioneering approaches, some more recent research direction has spread, and especially since year 2000, I would say, mostly. Two main areas in this context are named statistical relational learning and Neuro-Symbolic learning and reasoning. The distinction is not incredibly sharp, but mainly the difference is made by the presence of the keyword neural here. Basically, both these two fields have been developed between the 90s and the beginning of the century, and they both aimed to combine logic with, in general, sub-symbolic approaches. But while statistical relational learning aimed to combine logic with mostly statistical learning, okay, Neuro-Symbolic learning wanted to combine it with neural architecture, so cognitive neuroscience in general. There is also, I would like to point out, a third direction, which is very close in general to both first, which is made by purely sub-symbolic approaches, so purely connectionist approaches that aim to include knowledge within them, also to perform reasoning. This is clearly, I mean, again, the distinction between all these areas is not sharp. I will try to describe this better later. So statistical relational learning aimed at combining first-order logic and statistical learning mostly in the form of graphical models. For example, Markov models, Bayesian networks. And the goal was to exploit both, on the one hand, the expressive power of first-order logic, in general, first-order logic, but this is not necessary, and the capability of graphical models, or in general, of statistical learning approaches to deal with uncertainty. Clearly, this means to build frameworks that need to combine both logic and probabilistic inference. You cannot use just logical inference, because you have uncertainty in your data. You cannot only use statistical inference because you want to exploit logic. On the other hand, Neuro-Symbolic approaches wanted to use symbolic knowledge within neural architectures. This can be done in many different ways. This can be done by, for example, as we have seen in the knowledge-based ANNs, by encoding knowledge directly into the structure, into the architecture of the network. But this is not the only way to do it. For example, you can transform rules into a continuous function and use this continuous function as a regularization term for learning. There are many approaches that try to do that. So once you have translated rules into this continuous function, into this sort of penalty. Okay, you penalize networks that are trained but do not follow the rules in a sense. Okay, after you do that, do this transformation of rules, then the architecture becomes purely neural. Otherwise, another third kind of approach can constrain, in a sense, the computations of the networks with rules. Okay. Now here I have placed the two statements made by the major researchers in, I would say, in AI in general, but in this neural symbolic area for sure. The first is Luc Derat, whose idea is that the approaches that translate logic and place all this knowledge directly into the network and then let the network do all the rest, he suggests they should not be sufficient, because in a sense you lose what you wanted to use. So you lose the power of logic once you have made this translation. You lose the power of reasoning. You lose, in a sense, all the crystal clear explanation capability of logic. On the other hand, Yoshua Bengio supports the idea that instead logic inference or probabilistic logic inference is not so scalable. So if you really want to build systems that are able to perform on a large scale, in the end, the computations have to be neural, both for learning and for reasoning. Clearly, both these two statements have their reasons. There is nothing more to comment about that. We have to keep them in mind when thinking of the models we will describe later. So Neuro-Symbolic AI in general means a lot of different alternatives. You can have uncertainty modeled with directed models or undirected models. So Bayesian or Markovian networks, for example. You can use inference via grounding or via proofs. You may want to learn just the parameters of your logic model, or sometimes even learn the rules, so the structure of your logic model. Clearly, you can use different types of logic. Yeah, I mentioned first order logic, but you can use propositional logic, you can use horn clauses, and so on and so forth. And clearly also background knowledge can be modeled in many different ways. So this, what does all this mean? This means that many different frameworks have been proposed, as you can imagine, and there is not yet a standard, I would say. This also has repercussions on the tools that you can use. Many of the tools, if not any, all of them are still under development, are work in progress, are not so immediate to use for non-experts. This is clearly a key point. Let's briefly show a few examples of frameworks. So I'll start here from this model, which comes actually from statistical relational learning. At the beginning, it had nothing of neural, but I directly worked on this model, and I think it's quite easy as a first example to understand. So I'll start with this one. So this is called Markov-Logic networks. I'm sure that some of you knows them, and it's a probabilistic logic framework to be used to model knowledge. So you can have in a Markov logic network some constants that can have a type. For example, this is a list of movies, and then this is a list of persons. And you can have rules. For example, here you know that if person X likes movie M, and X and Y are friends, then maybe and here I say maybe because it's not always true, maybe also Y likes the same movie. Okay, it's not always the case, but it's possible because friends typically share interests. You can see that there is in fact a number that is attached to each rule. This is the second rule. That means that sort of transitivity of friendship. This is clearly questionable. Even symmetry, I think, friendship can be questionable, but transitivity for sure, because if X and Y are friends and Y and Z are friends, it's likely that X and Z are true, but it's clearly not always the case. So here is also a number attached to the rule. What does the number mean? The number means that the higher is the weight, and the more likely, okay, the more likely is a word. Here, word means an Hilbert interpretation, so clearly a grounding of all variables, where the rule is true, okay, all other things being equal. So the higher the weight, the more likely is the rule to be true in our interpretation. This is modeled by Loglinear model. So if we have a set of variables that we always that we want to infer, let's call them Y, and we have a collection of variables that we always observe, let's call them X. We have the probability of a word, of a configuration, depends on these weights. Depends on these weights and depends on the number of groundings of that formula. Now, I don't want to go too much into the details, but here you have basically the numerator of this fraction that models the probability. You have a product between the two terms. So the higher is the weight of a formula, and the higher is the probability. And the more groundings satisfy that formula, okay, the more higher again is the probability. Okay, so going back to the example, the more examples you have in your training data that confirm, for example, the transitivity of the relation of friendship, and the more this probability grows. What does it mean to perform inference? In this model, inference means to find the most probable Y given X. So to make a very practical and simple example, imagine that you observe, so you know that, for example, Alice likes Blade Runner, and you know that Alice is friends with Bob, and Alice is friends with Carl. What can you infer about the piece of knowledge that you do not know? So, for example, is Carl a fan of Blade Runner? What can you say about that? And this is the kind of question that you can answer with this model. You can perform both learning here, so you can learn the weights and the rules, okay, of your Markov logic network, and clearly you can perform inference. So given a list of facts, known facts, given the weighted rules, you infer the value of other facts that you didn't know in advance. So this is not neural, but a neural extension is something that I have worked on during my PhD, actually, and it's based on the idea that you can maybe compute the weights of the rules using a neural network. Okay, so in general, you would say this weight that for Markov logic in general is associated to each first order rule, okay, first order logic rule. Maybe we would like to have a different weight for a different grounding of the rule. And this is something that the neural network could compute. Okay, so in this case, we would say if example X has a set of feature F, can we say that his class is positive, for example, in a classification example? And we would like to compute this weight with a neural network. So we named this approach ground specific Markov networks. It was not yet the period of deep learning. So at that time we used plain shallow neural networks on a couple of applications in bioinformatics, in traffic forecasting. But nowadays we are reusing again this kind of models, trying to apply it to natural language. What is one very interesting property of this kind of models is that you can perform collective classification. This is something that is completely different from other learning frameworks in general. So what does it mean to perform collective classification? It means that your examples are not independent, like the friends in our example before. So if they are not independent, maybe you would like to classify them jointly. You may have these nodes in a network connected by edges and with properties, and you would like to predict the color of the nodes given the relations between them. So once that you have knowledge of the domain, once that you have knowledge of the relations between the entities of the domain, maybe you would like to perform classification in a collective way. And it is something that this kind of model can allow you to do. This is an example in text classification, for example. So you have these X and Y that this time are constants. So it's the syntax of Markologic is the opposite of the syntax of Prolog. So uppercase is a constant and lowercase is a variable. So for example, you know that with a certain weight, positive weight, X belongs to category A. With a negative weight, it belongs to category B. And maybe it's similar also for example Y, but you also have a rule that says if X and Y have certain features that they are also linked. This is also a neural rule. And you also have here at the end a constraint. Constraint is a rule with an infinite weight, which means that look, if X and Y have to be linked, it means that X has to belong to category A and Y belongs to category B. These are the only links that are allowed. So if you know that this property has to hold, probably this would change the classification that a neural network would perform independently on each of the examples. But jointly, you have to make this property hold. Another very recent framework that has been developed a few years ago is called Deep Problem by the group, the Leuven group. Is based on Problem. So Problem is a probabilistic extension of Prolog, where you can attach probabilities to ground facts or to rules. It has been used in a series of applications, performing basically probabilistic reasoning. And recently, Deep Problem was proposed by extending the syntax and the semantics of Prolog by computing probabilities with neural networks. This is an idea that is similar to the one shown before for Markov logic. Clearly, there is here a sort of a language barrier. You have to know Prolog, while in Markov logic, you have to just know logic, basically, first order logic. And here is an example from the Deep Problem paper. Imagine that you want to perform a query, okay, where you want to make the sum of these two digits, but you do not have the information of the digits. You only see the images, okay? You see this image, which contains a 5. We can see it's a 5, and an image that we see it's a 3. So you have to decode basically the information and to understand that the first image represents a 5, the second represents a 3, and you also want to perform the sum. So this is a neuro-symbolic task. You need both to perform pattern recognition, to recognize the shapes, the digits, and to perform the addition. And clearly, this additional knowledge that the addition rule has to hold may help the correction of errors of the pattern recognition part, because you cannot recognize, in general, you cannot say that the outcome of the addition is something that does not match the constraint, basically. If here, instead of the question mark, you had another digit, for example, you had the image of an 8, okay, you need to recognize all the 3 digits, and you have to ensure that the sum is clearly mathematically, arithmetically correct, okay? So you have both the pattern recognition task and the reasoning task. In general, the query would be correct even if you recognize a digit 0 instead of a 5 and the digit 8 instead of a 3, for example. But these would not probably match the recognition probabilities computed by the neural networks, because it's likely that the neural networks, as you can see here, may give a high probability to number 5, to digit 5, and a low probability to all the rest. Okay, so here in the syntax of DeepRoblog, you have what is called the neural predicate, which says, okay, digit is something that we want to be computed by a neural network. So whether digit X has value Y. So if digit X has value N1, is if it is a 3 or a 4 or a 5. Okay, and we also have an addition rule that is background knowledge and that must hold. Okay, so if we know that X is digit 1, that image Y is digit N2, then Z must be N1 plus N2. Okay, and you can perform this logical reasoning task by exploiting neural networks to compute the probabilities of some facts. Here is again an example in text classification. Later I will show a real application, not on DeepRoblog, but something similar to this kind of application. And you have basically to define these neural predicates. For example, here you say that these neural networks computes 3 possible categories, the probability of 3 possible categories. The second neural networks computes, for example, the probability of a link between these categories. And then you can write rules in this setting, purely logic or with a soft logic, probabilistic logic rules. For example, if X and Y have a link, then Y has to be of category A. Let's see another one. It's not the last one. I have another one, but it's very brief. Another framework called Logic Tensor Networks. Tensor Networks belongs to the field of approaches that basically transform knowledge into real valued functions, so into the structure of a neural networks inspired by these functions. They use fuzzy logic to do that. And then deep networks are used to predict the truth value of predicates. Here I have an example I think will explain better. Suppose that you have a rule that says that predicate, that we have a rule that says that if predicate VU holds, then predicate A holds for U. This can be translated into a rule where the inference, so the arrow is transformed into a disjunction, because we know that P implies A can be translated into not P or A. So the disjunction is transformed into a max operator, a maximum between two, you see, not P or A, okay? And these two predicates are computed via a neural network, okay? So we have a transformation induced by soft logic, and we have the neural architecture that resembles this structure inspired by logic. A final model that I want to briefly mention is close to logic tensor networks by the group, by the Siena group, Professor Marco Gori, which basically extends machines and neural networks by encoding rules and constraints that can be both hard and soft constraints into a regularization term, so a penalty term. We have you can write any kind of rules that you want. You can use P norms or any kind of other real valued functions to transform these rules into a real valued function, and then you use this as a penalty during training. And so the network is forced to learn in a way in which rules are satisfied. Okay, so in a sense, you penalize solutions where your constraints are violated. And this is something that has many connections with the approaches that I have presented earlier. Finally, I have mentioned what are purely sub-symbolic approaches. So where rules is not sometimes even explicit, they can use auxiliary memories, for example. These are called memory enhanced neural networks, where you store in a memory in some sub-symbolic form some sort of knowledge. I will show an application of this in a few minutes. Or you can use what is called distillation from larger to smaller models. For example, quite famous work consists in having two networks, a teacher and a student. And the teacher networks is trained also using soft logic rules. Is trained for a certain task, okay, for any kind of task, and the student is trained not for that specific task. Is trained to replicate the behavior of the teacher. Okay, so this is called, in a sense, distillation of knowledge from the teacher to the student. And this is interesting because very often it happens that the student network, we can observe it can be thinner, smaller in number of parameters with respect to the teacher network, okay? But this is something that we have no time to talk about. I have at the end of the presentation all the references to these works, so for those who are interested, clearly you can ask questions, so you can write me an email, and I will be happy to share some material, even the presentation, of course. So we know that many applications have been developed for deep learning. This is not exactly the case also for neural symbolic learning, because mostly this kind of approaches, when first introduced, are used on toy problems, for example, for probabilistic reasoning. They have been used, yes, for some image classification task, for example, to respect some taxonomy, some rules for knowledge graph completion, but some large-scale application really still has to be implemented. I'm particularly interested in natural language processing, and I will present now a couple of applications that we are working on neuro-symbolic approaches, or in general approaches that use knowledge for NLP. So the first one is argument mining. For those of you who do not know argument mining, this means to extract arguments from text in general. Where an argument is, there are many definitions of argument. One of the simplest, given by Walton, says that an argument is a statement named a claim, supported by some premises. Okay, and you also have an inference clearly process from premises to the claim. Okay, this is a very tough task because you have to detect the argument components in a text. You have to detect the links between argument components. This is an example of an argument taken by a famous corpus developed by IBM. It says there is a claim that says health risks can be produced by long-term use or excessive doses of anabolic steroids. This is a claim and is supported by a premise that says that a recent studies has also shown that blah 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 long-term steroids users were more likely to have symptoms of dysmorphia, muscular dysmorphia, for example. So you have a claim and a premise that supports the claim. And it's difficult, clearly difficult, to detect this kind of portions of text and relations between them in unstructured text. One of the goals of argument mining is to build what is called an argument graph. So you may have a long piece of text and many claims and many evidence or premises connected between them. So you may have an evidence that supports this claim and another evidence that supports another claim. And maybe this claim attacks one another. Okay, this is called an argument graph. So building these argument graphs is the ultimate goal of argument mining in general. It's difficult, but it's interesting for neural symbolic learning, we believe, because there are rules that can be enforced to build the structure of this graph. For example, you can say that if you have a fact X that supports Y, so if there is a supporting link between these two entities, according clearly on your argument model that you are using, it's very likely that X is a premise and Y is a claim, and not the other way around. Or maybe if it is X that supports Y, then it should not be the other way around. You should not predict that also Y supports X. And maybe if X supports both Y and Z, if this supports two claims, then these two claims should not attack each other because they are supported by the same premise. Okay, it would not be a correct way of arguing. In other cases, rules can be soft, so not hard constraints based on the model, but it can be, for example, if you have a political debate and you have, I don't know, the candidate of the Republicans and the Democrats, maybe if there are two claims of these two political opponents, it's very unlikely that they support each other. Much more likely they attack each other. Okay, and so this is clearly a domain where you can write rules, but you want also to use standard NLP techniques because deep learning has produced so many stunning results in NLP as well. So we made a preliminary experiment with logic tensor networks, and we believe this is one of the first applications of the logic tensor networks to NLP in general. We have used a small corpus because scalability is an issue, unfortunately. We have to be honest about that. It's still an issue in this kind of models, so we have used one of the smallest corpora. In the field, we have basically abstract of randomized clinical trials papers, and we have data set where we have different topics, neoplasm, glaucoma, etc. And the part of link prediction is particularly difficult because only 10% of the pairs are linked. And we can enforce rules in our model. So these are some of the rules that I already talked about. So if X and Y are linked, then Y and X should not be linked because this supporting relation is not symmetric. Or the argument model is made in a way that a claim can only support a claim, not an evidence, and the other way around, an evidence, so a premise, can be supported only by an evidence. So using these rules, we have obtained an advancement over the performance of a network that is trained only on pure data. Okay, so you can compare here the rules that are data or data plus rules. Okay, for each different test set. Okay, we have two numbers because we have used two ways of aggregating the predictions of the networks. This is not so important now. If you are interested, we can see these details later. But you can observe a significant improvement, especially in the link prediction, so between the first row and the second row of each block, basically. While for components, the performance are similar. The satisfaction of properties was already very close to 100%, also for networks only trained on data, but it goes to a perfect match for the network, the LTN trained with the rules. So in the LTN frameworks, these rules are always satisfied. The second and final thing I want to present is an application of this kind of approach to legal informatics. With many colleagues at the University of Bologna and the European University Institute in Florence and other colleagues in Europe, we have worked in the last 4 or 5 years to a very interesting topic, I think, that is at the intersection of computer science and the law. And basically, our idea was to build instruments to empower consumers. So we know that AI is very often used by business against, in a sense, consumers, because they can hurt our privacy, they can provide unfair advertising, aggressive advertising, they can sneak unfair clauses within online contracts. So our idea is that AI should instead be used on the side of consumers. And one of the applications that we can imagine in this context is what we have tried to do, is to detect, in fact, potentially unfair clauses for the consumers in online terms of service contracts. So, you know, every time that you subscribe to a service online, you have your terms of service in front of you, you always click on the next button, accept button, and you do not even read the contract. I mean, everyone does the same way, I'm pretty sure. But it happens, my colleagues in the legal domain have taught me that these contracts very often contain potentially unfair clauses for the consumer. Legal experts are can recognize them because of their knowledge, domain knowledge of the law. Can we use such a knowledge also in an AI system? So can we use all these? These are not exactly rules. It's really a collection of knowledge, of experience that the legal expert has acquired through the years. Can we use it to infer whether potentially whether a clause is potentially unfair. We could clearly frame the problem as a purely an classification problem for NLP, but we would like to use this information that the legal expert has. Here is an example. You have a clause in a contract which says with new products, services, and features launching all the time, we need the flexibility to make changes, impose limits, and occasionally suspend or terminate certain offerings. Now, this is not an unfair clause for a non-expert, I think. Seems reasonable for me, but it's actually absolutely not fair. Not fair because what is the legal rationale behind this unfairness? Is that the clause is potentially unfair because the provider here has the right for an unilateral change. And this is not allowed by the law, unless there is explicit consent, basically, of the user. So this kind of legal rationale is an explanation, is the reason for which the clause is unfair. Can we use this information in a neural network? Now, what we asked our colleagues, our legal colleagues, to do is to find for 5 unfairness categories regarding arbitration, regarding unilateral change, content removal, etc. Not only the list of unfair clauses of the list of contracts, but these rationales. They found 8 different rationales, for example, for the category of arbitration. So 8 different reasons of unfairness, up to 28 for unilateral termination. So there can be many different reasons for which a rule is not fair. And these rationales, we have decided to use them into a memory. So what I described here is really a purely sub-symbolic approach. Okay, there is no explicit logic formulation in there. We have implemented an external memory with all the legal rationales given by experts. We use what is called attention in natural language processing to retrieve the content from the memory. And then when we perform classification, we use both the input query, the clause, and the content retrieved from the memory. We can use this information from the memory in 2 ways, what is called weak and strong supervision. It's called the strong supervision, basically, if you exactly know for each clause which is the corresponding explanation. Here is a figure of the architecture. You have here the list of the rationales, for example, for arbitration. Okay, so the consumer must first opt out for the arbitration not to be obligatory. This is 1 memory slot up to the last one. You have the query, which is the clause for which you want to predict whether it is unfair or not. You basically compute a similarity between the query and the memory. You extract content from the memory and you perform your classification. So it's called the memory enhanced architecture. We have performed experiments on 30 contracts, and we have seen that our model that can be combined both with BERT and with other NLP approaches performs quite well, better than plain natural language processing classic approaches, is close or sometimes better than plain BERT. But the interesting property clearly here is that you can interpret the result. So once you get the result of your network, you also know why the clause was predicted to be unfair. And in particular, we have measured this with many different metrics. Now I don't want to go into the details, but if we focus on this column here of the table, so the precision P at 1 here is called, so basically the top scoring memory slot, so the explanation, if you have to use just one, most likely for the network, we can observe that we have, using strong supervision, a performance that is very high, close to 80–90%. This means that 80–90% of the times, when you predict a clause to be unfair, you are also able to explain why the clause was unfair. This is a feature that is crucial in many domains, not only in the legal domain where is very welcome, but also in other contexts. It could be in medicine, it could be in other scenarios where clearly interpretability is a crucial issue. We have implemented, and then I come to conclude my talk, we have implemented this framework in a web server that you may want to have a look at. It's called Claudette, from the name of the project that we have been working on. You can you can submit to Claudette a piece of text or taken from an online contract, and you can obtain, you see the prediction of Claudette that, for example, in a piece of text says that this clause is potentially unfair, and it explains to you why, which are the rationale that are behind this classification. Okay, so you have these three explanations, each with a different score. So that's the server that is available. So to conclude here, I just want to briefly recap a couple of things that I already insisted on. So this is a very exciting area, I think, Neuro-Symbolic AI, with many challenges ahead, because many of the approaches are basically still in their infancy, because there's a lot to be done in terms of scalability of the approaches, in terms also of relations between the different approaches, because there is not a clear taxonomy. Unfortunately, and I have to say this is a barrier at the beginning, there is no off-the-shelf tool ready to use at the beginning. You have to play a lot with existing repositories and tools in order to be able to use them for some experiments. And this is also a reason that makes the research in this area very exciting, I think. It's very important because it's clear in the direction of explainable AI. And this is so important, I think, in these days for many also reasons that deal with ethics and fairness and in general. We have many ideas for benchmarks and for also real world problems and domains that can be used for this kind of applications. I think that in this sense there are reasons, to also collaborate for the logic programming community, because I think this is a common issue. And here are some references that I can leave here. I can leave the presentation to the organizers for those who are interested. Okay, thank you very much for listening, and that is any question.
Thank you, Marco, for your nice presentation. Very interesting. There is time for some questions. So if you have questions, please raise your hand. I don't see any questions. So yeah, there is a question from Parma here.
Yes.
Hello, hi. Just a very general question. You said that there is no real benchmark to compare those approaches. But did you try on a real world example to verify if the use of logics can help the performance of in performing the task of your system, or in the end it ensures explainability and it ensures some correctness, but does not really help from a performance point of view? Thank you.
Yeah, thank you for the question. I was very quick on one slide where I can show this. I can go back to this. Okay, here is the performance of our system. I can go screen again. Here is a real world task where you have 30 contracts, 30 terms of service contracts, and you want to predict whether a clause in the contract is unfair or not. And you can do this in a pure sub-symbolic approach, so with NLP approaches, like the ones that are shown here on top, that do not use knowledge. So convolutional neural networks, long short-term memory networks, or Distilbert, which is a state-of-the-art model. And you can use networks that exploit knowledge. For example, here you can see that on the arbitration case, clearly the networks that use also knowledge are much better than the plain sub-symbolic approaches. In other categories, it's almost on par, the performance, but on average is slightly better with knowledge. Clearly, you have to consider, yes, that you have here two distinct tasks, so both performance and explainability. So in a sense, you see slightly better performance of the neuro-symbolic approach, and you also can observe an explainable answer. I hope this answers the questions. This is the larger application domains, the domain that we have tested so far. Also in argumentation mining, we observe a similar task, but it was a smaller size corpus.
Thank you, Marco, for answering the question. Is there any other question from the audience? Okay, so yeah, I see a raised hand by Laura Giordano, please.
Hi, I have a curiosity. When you are talking about collective classification, you mentioned a case where you have to predict the color of the nodes, given their relationship. Is this an example in which so your domain has some structure that would be exploited, for instance, in a graph neural network? But you were talking in that case about Markov-logic network, actually. Is there any relation?
That's a very good question. That's a very good question, actually, because clearly every time that you have a structured domain such as a graph, you could perform classification with the graph neural networks. Graph neural network typically associate label to a graph in general. They can also use to associate labels to nodes, but the difference here is that in a neuro-symbolic framework in general, you can model the relations and background knowledge in general through logic facts. While a graph neural network is purely sub-symbolic, so it learns in general underlying patterns from the structure of the graph. On the other hand, with a neuro-symbolic approach, you can model knowledge of the graph in an interpretable way. So this is the difference. A GNN would be a competitor, if you want, in that case. A strong one, I would believe.
Thank you very much for your answer.
Okay. Is there any other question? If not, I think we can thank Marco once again. And now for those who are here in Parma, there is a coffee break in the same room as yesterday. And for everyone, we can meet here at the same virtual room, the same link, at 11:30 for the third session of CILC. See you later.
Thank you. Bye.